Hello and welcome to the chapter 3.1 Uniform Circular Motion presentation. So what will this presentation be about? What we'll be learning? Hopefully we will be understanding uniform circular motion in terms of the force that acts on an object in a perpendicular direction to the velocity of the object, and by the end of this presentation you should be able to understand the forces operating on an object that is revolving in a horizontal plane. Take a minute to think about why we're considering a horizontal plane for circular motion rather than a vertical plane. So, first of all, we're going to think about what is uniform circular motion. Simply, it's moving at a constant speed, so not speeding up or slowing down, in a circle. Can you think of any examples? There are plenty in everyday life. You can see there's a fidget spinner here. We've also got the Earth that moves in a circular orbit, ceiling fans, fairground rides, washing machines. I'm sure you can think of some more. So one thing that comes up when we think about circular motion is the difference between revolving and rotating. So what is that difference? Often we think about these terms in terms of the Earth, so you will hopefully have come across it in the junior years in Earth science. So revolving is moving in a horizontal circle around the axis of a second object. Orbit's often used in place of revolve. Rotating is when an object moves in a circle on its own axis. So if we think about that in terms of the Earth rotates on its own axis. That's what gives us day and night. And then once a year it revolves around the sun. Does the Earth move uniformly in a circle? Not completely. The Earth's orbit is actually an ellipse, and that causes some variation in the length of seasons and other things. So the force we're thinking about today is the centripetal force. If we look at this diagram and have a think, what way does the plane want to travel? So if we think about Newton's first law, the plane will want to travel in a straight line. However, it's stopped from doing so by the pull on the string in the boy's hand. So the pull force on the string will always be towards the boy's hand or the centre of the circle, and therefore it's called the centripetal force, which is written as FC. Centripetal means searching for the centre, so it's always pointing towards the centre. The definition of centripetal force is the force acting on an object travelling in a circle that constantly either pulls or pushes the object towards the centre of motion, and its unit obviously is newtons. So now we're considering the velocity in the circle and centripetal acceleration. So we can draw the velocity at any point on a circle as a tangent to that point. So if we look at point A here, we can see the velocity is pointing northwards if we draw a tangent. That's V1. If we look at point B, again, the velocity is a tangent. You can see the arrow is the same size. So what does that tell us about the speed? It tells us the speed is constant. It's travelling at the same number of meters per second. But what does it tell us about the velocity, the vector quantity? We no longer, every time the object moves in a circle, its direction is changing. So from the diagram, could we say the velocity is constant, or would we say the velocity is changing? We can see that the velocity is changing direction, and that means the velocity is in fact changing. So does that mean that the object is accelerating? And the answer is yes, it is. And the type of acceleration is called centripetal acceleration. And that's the acceleration experienced by any object moving in a circular path directed towards the centre of motion. We write that with the symbol A subscript C, and it has the units of all acceleration, meters per second squared. So what's it like when we experience the centripetal force ourselves? One example where we do is a ride like a graviton or a rotor, where you feel pressed against the wall. What's actually happening is, due to the spinning of the ride, your weight is being pulled outwards away from the motion, and the wall is exerting the centripetal force on you. The centripetal force is actually like the normal force that's being directed radially inwards towards the centre of the ride on you. At high speeds, as many of you will know if you've ridden these things, the force is great enough to provide friction to stop you from sliding down the wall, even if the wall is moving into a vertical circle away from a horizontal circle. There isn't actually a force pressing you to the wall. You're just trying to travel in a straight line, and the wall is preventing that from happening. So next time you're at the fair, you can think about that. In the meantime, you can go to page 97 of your textbooks and check your learning. Now we're moving on to chapter 3.2 and considering what happens to objects that are undergoing uniform circular motion. So what we're going to learn about today is average speed of an object travelling in a circle and its period, and also how to solve problems that involve average speed of objects in uniform circular motion. You'll know you've achieved that if you can understand the difference between average speed and tangential velocity and rotational speed, and also if you're able to do calculations using the formulas for period, time and tangential velocity. There's a great meme there. Of course, earth science is the best science. Okay, so to help us get some grounding in what we're going to cover, let's think about definitions. So average speed, or V, of an object in a circle is no different to speed in any other situation. It's the distance travelled divided by the time of travel. Distance in the case of the circle is how far you travel as you move around the circle, and it's equivalent obviously to the circumference, which is given by 2 pi r, where r is the radius of the circle. Period we've come across before in waves. It was the time taken for a wave to pass. In the case of a circle, it's the time taken for one complete revolution around a circle from one point and back to that point, and that has the symbol t. With this in mind, average speed for an object in uniform circular motion is given by the expression distance over time, or 2 pi r, circumference over t period. This speed is sometimes called the tangential speed to distinguish it from rotational speed. It's also called tangential velocity. Okay, so let's try those equations we've got for period and average speed. So a girl whirls a ball on a string in a horizontal circle. The length of the string is 2.2 meters, that's quite a long piece of string, and the time for one revolution is 3.1 seconds. So first we need to calculate the period, then the average speed of the ball, and then we need to think about the velocity of the ball. So what do we know? We've been told that r equals 2.2 meters, and we know that the time for one revolution is 3.1 seconds. So if we think about that, the formula for period, it's t equals time, so 3.1 seconds, over number of revolutions, so we know that's just 1, so t equals 3.1 and the units are seconds. For velocity, question B, we just use the equation 2 pi r, which is distance over time. So we plug in the numbers that we know into our calculator, so we'll write them there, 2 times pi times 2.2 divided by 3.1, and that gives us 4.5 meters per second. That's the speed, but what about the velocity? Well, what direction is the velocity pointing in a circle? Well, at every point it's directed towards the center of the circle. So for the velocity, we would give it as 4.5 meters per second directed towards the center of the circle. We can see the response there with my scrolling over the top. So we've considered average speed. Let's now move on to thinking about rotational speed. Do you know the speed of the moon? Perhaps you do. It's not something that many people would know. It's not something given in kilometers per hour, meters per second. But most of us are probably aware that the moon makes one orbit or revolution of the Earth every 27 and a bit days. So it's sometimes given as 28 days. So that's something given as a rotational speed rather than average kilometers per hour speed. Can you think of other things that are given as a speed of rotation? I'll give you a clue here. So this is something you may have on your dashboard if you're driving, and it's giving you an indication of your engine speed, so how many revs per minute your engine is making. A typical engine, when it's idle, has a rotational speed of about 750 revs per minute, and if it's at cruising speed, it goes up to 4,000 revs per minute, depending on the car. Whereas the moon's rotational speed, as I've said, is about 1 rev per 27 and a bit days. So rotational speeds are measured in the number of revolutions per unit of time rather than a specific distance per unit of time. And average speed is more of a linear speed. It's not revolutions per second. So using rotational speeds to make some calculations. Rotational speeds can be converted into the time for one revolution using the formula of period equals time over number of revolutions. So let's think about example 3.2. Calculate the period for an object with a rotational speed of 30 RPM. So we want to know t. We know that we've got 30 revs per minute. So a minute, we're giving our time in seconds, is 60 seconds. And the number of revolutions is 30. So our period in this case will be 2 seconds. Okay, we've got the answer there in case you don't trust my working. So let's apply this to a slightly more complex problem. We've got a car tyre with a diameter of 630 millimeters that is being rotated at 850 RPM on a tyre balancing machine. And we've been asked to determine the average speed of the outer edge of the tyre. So the formula for average speed is V equals 2 pi r over t. So we need to determine r and we need to determine t. So r we know is half the radius, half the diameter is the radius. So 630 millimeters gives us 0.63 meters divided by 2. So r equals 0.315 meters. Next we'll calculate t, which is equal to time, which is going to be 60 seconds because we've got revs per minute, divided by number of revolutions, which is 850. So t is going to be 0.07 seconds. So pretty quick revolution made there. Let's plug those into the average speed equation. V equals 2 times pi times 0.315 divided by t, which is 0.07. Plug those into your calculator and you will get a value of 28.3 meters per second. So the average speed would be 28.3 meters per second. You can see that underneath my messy writing there, or in your book on page 100. So a practical application of circular motion is the centrifuge, which is used in numerous science labs as a way of separating suspension, so a solid suspended in a liquid, or immiscible liquids that don't fully mix together. So that's what they're used for. I've given away the answer to the first part. But how do you think they might work? How does centripetal acceleration cause the separation? So if you look at the picture there, you can see that you put tubes in and they are able to flip out, so they are horizontal as the centrifuge is rotating at speeds of between 1,000 and 5,000 revs per minute. So think about what might happen. You might want to pause this, or you might already have it in your head. When the test tubes are spinning out horizontally, the most dense, heaviest material will, due to centripetal acceleration, move out to the farthest end of the tube, while less dense material will move towards the centre of rotation, and that will separate it out. One thing that's commonly separated in a centrifuge is blood, and that's what you can see there. At the bottom of the test tube you have the blood cells and the proteins, and then at the top you have the plasma or the serum, and that's very useful in medicine. Okay, so time for another worked example. This one considers how you can affect the speed of a tumble dryer, either by doubling the diameter of the drum of the dryer or doubling the rotational speed. So dryer A has a tub of diameter 50 centimeters and a rotational speed of 1,250 RPM, and dryer B has a much larger diameter of 115 centimeters and a lower speed of 635 RPM. Roughly speaking, the speed of B is half the speed of A, and the diameter of B is twice the diameter of A. So first of all, we need to determine which dryer will have the highest speed, and then propose which would be preferred for household laundry. So what we first need to work out is the period for both dryers. So if we remember that we start with A, need a better colour there. T of A is going to be equal to time, which is given here in minutes, but we need to convert that to seconds, so that will be 60 over the number of revolutions, which is 1,250. We plug that in to the calculator, and that gives us a period for A of 0.048 seconds. We then do that for B. Again, we're in revs per minute, so the time is going to be 60 seconds over the number of revolutions, which is 635. Plug that into your calculator, and we get a period for B of 0.094 seconds. Now we need to put that into the average speed or average velocity equation. So if we remember that, it's V equals 2 pi r over t. So for A, that's equal to 2 times pi, and for A, the diameter we're given is 50 centimeters, but we need a radius. So we need to first of all convert it to meters, so it'll be 0.5 of a meter, then convert it to centimeter to radius, so divide it by 2, that gives us 0.25 over t, which we've calculated over here as 0.048. That gives us the answer of 65. Oh, actually no, the answer in the book is wrong, so you need to plug that into your calculator, and that comes out as 32.7 to 3SF, as it's given in the figures are given in the question, and the units is meters per second. Then if we do B, again we've got 2 pi r, so 2 times pi, and the radius in this case is given, well, we've got a diameter of 115, so we need to divide it by 2 and also divide it by 100 to convert it to meters, and that gives us 0.575 divided by the period, which we got here as 0.094. That gives us a velocity of B of 38.43. So now we think about what does that mean about the dries. So the dries have roughly the same average speed or tangential speed. If the speeds were different, the dry with the faster tangential speed would dry the clothes more, but it might cause more creases. One thing in terms of the diameter, a diameter of 115 centimetres might not be very practical for a dryer. It wouldn't fit in a lot of laundries. So I think usually you would find a much smaller drum than that. So we'd go with a higher rev per minute. So there's the solutions hidden underneath there, but you will see that if you look at that in your book on page 101, there are some errors there. So have a go now at the Check Your Learning, which is on page 102. Okay, so finally we're on to the sections of chapter 3.3, which relates to centripetal. So what are we doing today? Well, we're going to learn about centripetal acceleration and centripetal force. We've already learned about the definitions of those things, so we're going to do some calculations relating to them. And we're also going to solve problems that involve forces acting on objects in uniform circular motion, including the average speed of objects undergoing uniform circular motion. How will we know whether we've succeeded? Well, in order to do this kind of calculation, we need to be able to subtract vectors that we haven't done before, so hopefully you'll know how to do that. And you'll also be able to use those resolved vectors to calculate centripetal force and centripetal acceleration. So let's think about the forces acting on an object in uniform circular motion in terms of both acceleration and force. If we look at this diagram of a hand rotating a ball on a piece of string in a round circle, let's think about what's keeping the ball moving in terms of force. So in order to keep the ball moving, you must apply a force with your hand. I'm sure lots of you have done this, or if you haven't, you can have a go at it when you get home, or right now if you want to. That force is actually unbalanced and it's directed inwards in the circle. Because there is an unbalanced force, that must mean that the ball is accelerating inwards according to Newton's second law, force equals mass times acceleration. Is the ball accelerating then? Because we've said it's going at uniform velocity. But if it's accelerating, something about its velocity must be changing. And we discussed previously that a ball can accelerate without changing speed, but by changing its direction, because we're talking about velocity, a vector quantity. What does this mean about its velocity, assuming uniform circular motion? So what we can say about its velocity is that the speed is constant, it's travelling at the same average speed in terms of meters per second, but the direction is constantly changing as the ball moves around the circle. The formulas relating to centripetal acceleration and force, or the formulas that relate centripetal acceleration and force to average speed of an object that is travelling in uniform circular motion are a bit trickier than what we've met previously when we've been looking at linear motion, because they involve vectors in 2 dimensions. And they also require that you subtract vectors, because the acceleration is a change in velocity and change means subtraction. Where we've been resolving vectors in 2 different directions to date, we haven't had to subtract them, we've actually been adding them. So before we move on with calculations of centripetal acceleration and force, we need to think about how do we subtract vectors. So, the subtraction of vectors. How do we measure the change in speed that we see in a circle? change in measurement equals, well, we always use the same equation, the final measurement minus the initial measurement. Change in speed, therefore, will be the final speed minus the initial speed, or delta V equals V minus U. The Greek symbol delta is always used to represent change. It means difference, and we've come across it lots of times before. So this is true for scalar quantities, but now we're thinking about vector quantities where we have direction as well as magnitude. Okay, so how are we going to subtract vectors? Well, let's think about a simple linear motion equation. We've got an object travelling from left to right at 15 meters per second in its final velocity, with an initial velocity also from left to right of 10 meters per second. That is equivalent to, if we have a final velocity of 15 meters per second and we add it to initial velocity that was going from right to left rather than left to right, so it then becomes a negative velocity. So what we're doing is the velocity we're subtracting, we're adding it, but we're putting it in the opposite direction. So when we put those two together, it's 15 plus minus 10, which gives us plus 5. And you'll see why we're doing this when we come to trying to resolve these things in a triangle rather than on a straight line. That's when it gets more complicated. Alright, so let's apply our newfound skills in subtracting vectors to a problem. So a girl is travelling north 10 meters per second, and she turns left and carries on west at 15 meters per second. So if we remember from the last slide, delta V equals final velocity, which in this case is 15 meters per second west. We instead of subtracting, we're going to say plus minus 10 meters per second north. If we resolve that, that gives us delta V equals 15 meters per second west plus 10 meters per second south. We can now draw a new diagram to represent our velocities. So if we're going south now, so 10 meters per second south, and again still 15 meters per second in the westerly direction. That gives us this resultant velocity, or delta V. Now, in order to determine this value, we need to use trigonometry, and we also need to figure out what angle this theta will be to give us the direction of this velocity. So first of all, if we have, as we do here, the adjacent and the opposite, it would make sense to use Pythagoras to calculate this value here. So V equals the square root of 15 squared plus 10 squared, which works out to 18 meters per second. That's to 2 decimal places, which is equivalent to what we have here of two significant figures, because we have 2 significant figures here and 2 significant figures here. We now need to determine the direction, because, as I've already said, we have opposite and adjacent. Tan is our friend. It's better than putting in a calculated value, which we may have made a mistake on. So tan equals opposite, which is 10 over adjacent 15. So theta equals 34 degrees. So our final answer will be the resultant velocity is 18 meters per second at, in a direction of 34 degrees south of west, and we're able to understand that direction because of this method we've done here in subtracting vectors. You'll notice, if you can see underneath my scroll, which I know is not a patch on Khan Academy, that they give their final answer as 20 meters per second, saying it's to one significant figure. But from what we've understood about questions, if you give the answer to the correct number of significant figures and all the numbers in the question, which are 2 significant figures, so I think 18 should be the answer there. Okay, so we've thought about changing velocities, changing velocity directions, but if we have a look at this free body diagram of forces acting on a revolving object and we compare u and v, we can see that these velocities, which are tangents to the point, are equivalent in terms of their magnitude, but they are different in terms of their direction, and that change in direction means the object is said to be accelerating. So how could we calculate A, given that we've got this u and v? Well, we can use the equation acceleration equals change in velocity over time, and therefore change in velocity, as we know, is final velocity minus initial velocity divided by the time taken for that change to take place. But we have to remember that these velocities are in 2 different dimensions. They're not linear, as we dealt with last term. One is to the north and one is to the west. So the magnitude and direction of this acceleration can be calculated by determining the change in velocity by subtracting vectors. So let's use what we've learned about deriving resultant velocities by subtracting vectors and use that to help determine centripetal acceleration. So recapping about the third time, change in velocity equals final velocity minus initial velocity. How do we subtract vectors? We say change in velocity equals final velocity plus the negative of initial velocity. Get that negative by reversing the direction of u. So if we look at this top diagram here, we see that u is pointing upwards. If we look at the resolved vectors, we see that u is now in the downward direction. What we do notice is that resultant velocity is pointing to the centre of the circle. If we impose this onto the circle that we saw in the previous slide, we'd notice that this points towards the centre of the circle, and that's why centripetal is used in this context, because it's the Latin for centre seeking. So let's consider some other variables. The time taken for an object to move from A here to B here is delta t. So what's the distance? Well, we know that velocity equals distance over time. We can rearrange that equation to give us that distance equals velocity times multiplied by change in time. Now, as in this case, we've got a short chord rotating an object around a central point. Well, in this case, the object is a ball. It's reasonable to assume that the length of the chord S is equal to velocity times delta t. That's not always the case. We can then use similar triangles to find an equation for A, because this triangle here with the resolved vectors is equivalent to a triangle here where we have S distance and the 2 radii of the circle. So therefore we can say, looking at this one, delta V over V is equivalent to S over R. We can then substitute in this equation here that we've got for S, so delta V over V equals V delta T over R. And we can rearrange that further to give us delta V over T, which is an equation for acceleration, and therefore centripetal acceleration, or A subscript C, is equal to V squared over R, where R is the radius of a circular path in meters, in this case a piece of string, or the length of the piece of string. Now it's interesting to note here that when we look at this equation, A is proportional to V squared. And that means that it's 4 times harder to go around a corner at 100 kilometers per hour than it is at 50 kilometers per hour. So you may have encountered that challenge when you're riding on a bike or driving in a car yourself, or you might be thinking about it next time you go around a corner. Certainly something to think about. So let's apply that to a worked example. A rubber stopper on a piece of string 1.5 meters long is whirled in a horizontal circle at a uniform speed of 2 revolutions per second. Calculate the average speed and calculate the centripetal acceleration. So the first thing we need to do is calculate the period. So if we remember, period equals time, which in this case we've got revs per second, so it would be 1 over the number of revolutions, which here is 2. So t will equal 0.5 seconds. We've got 2 decimal, yeah. Trying to think, should that be 1 or 2 SFs? Probably just 1 SF. But we'll do it to 2. We'll then put that into the velocity equation where v equals 2 times pi times r, which we've got here, 1.5, and it's in meters, which is the units we need it in, divided by t, which we got here, 0.5. And that gives us a value of v of 18.8 meters per second. Oh, I said average velocity. So we can then put that into the acceleration equation that we've just derived. So AC equals v squared divided by r. Plug in the values we've got. So v squared 18.8 squared divided by r 1.5. That gives us an acceleration of 237 meters per second squared. Directed towards the centre because it's centripetal acceleration. Have a think about what that should be in significance is, and I'll reveal it for you now. So this is an extension thing for you to consider in terms of rotational speed. The radian per second, given in symbols rad per second, is the SI unit of rotational speed, commonly noted by the Greek letter, looks a bit like a W or omega. Some of you in maths may know that there are 2 pi radians in a circle of 360 degrees, and engineers use radians per second when working out the power of rotating shafts. So you might want to determine how many revolutions per second 1 rad per second is. You might also want to think about not accidentally putting a calculator in rads when you're in physics, because we don't use rads at the moment in physics. We've thought about centripetal acceleration, so let's move on to centripetal force. What force is a ball on a piece of string being whirled horizontally in a circle experiencing to keep it moving? That's called the centripetal force. We've talked about it in the previous couple of chapters. And this law is provided, this force is provided by the tension F net in a string. Which Newton's law do we use to help us understand this? F equals mass times acceleration. So the centripetal force equals mass times the centripetal acceleration that we've just been working with. The net force is equivalent to the mass times velocity squared divided by r if we substitute in the equation we derived earlier for centripetal acceleration. Note, for horizontal circular motion, the net force is equivalent to the centripetal force. This is not true in vertical circular motion because we have acceleration due to gravity acting on it. When Isaac Newton proposed the laws of circular motion in his Principia in 1687, he wrote, "Centripetal forces acting on bodies undergoing uniform circular motion are proportional to the square of the arcs described in a given time, divided by the radius of the circle. He was a very clever man, that Newton, much cleverer than Donald Trump. Let's apply what we've learnt so far and put it into an equation to work out centripetal force and net force. So a rubber stopper of mass 20 grams is whirled in a horizontal circle at a constant speed on a string that's 1.5 meters long. This is the same as the last worked example we were doing. If the average speed, as we calculated, is 18.8 meters per second, let's calculate the centripetal force and the tension in the string. So first let's start by writing what we know. So M equals 20.0 grams. Think about that unit, is that right? For the calculations we're doing, R, or the length of the string, is equal to 1.5 meters, and V, or average speed in this case, is 18.8 meters per second. Grams are not the correct units in this case. We need to convert it to kilograms, so divided by 1,000, that gives us 0.0200 kg. We're given these two zeros because we've got these two here, so they're significant. Alright, so let's put that into the equation that we got on the previous slide, remembering that the centripetal force is equal to the net force in horizontal circular motion, and net force will be equal to the tension. Therefore, the force is going to equal mass times velocity squared over r. Plug in the numbers that we've put above. So 0.0200 times 18.8 squared divided by 1.5. That gives us a value of FC, or F net, of 4.7 newtons. If we think about how we would finally word that, the centripetal force is 4.7 newtons directed towards the centre of the circle. That's a vector, so we need to give the direction there, and the tension in the string is 4.7 newtons. We don't need to give a direction, so that would be written as F net equals 4.7 newtons. It doesn't have a direction, it's a scalar quantity. You can see under there, it's written under my sprawl. So let's think of a practical example of this centripetal force and centripetal acceleration. It's skidding, or going around a curve safely, I should say. So a racing car is travelling around a circular track in a similar way than a ball on a string is travelling around in a circle. A vehicle taking a corner on a level road can be viewed as though it's going on a circular path. What force is keeping the car on the circular track or a tight curve on a road? What's providing the centripetal force? Have a think about it. You can pause that if you want to do some research, or you can carry on listening. So friction provides the centripetal force. If there's a wet patch on a corner, what will happen to the centripetal force and the car? Think about that. So the car, rather than carrying on around the circle, will tend to go straight ahead in the direction it's travelling, or spin out of control. So the friction between the tyres and the road is providing the friction needed to stop the car just going straight ahead, as Newton's law would suggest it wants to. On a wet corner, the friction is reduced, and there would be insufficient centripetal force to keep the car on its circular track, and as a result the car would spin off, as this one's doing in this picture here. So let's think about this practically and do the maths of going around a corner safely. The maximum safe speed to go around a curve is when the average speed requires a centripetal force equal to friction. For a car with rubber tyres on a dry bitumen tar road, friction is typically 70% or 0.7 times the car's weight. So let's calculate the maximum velocity, the forces at which the forces will balance and the car will not skid out of control. So in this case, the centrifugal force will be equal to the friction force. It should be FF on FT, sorry. So mass times velocity squared over R will be equal to 0.7 the weight, which is mass times G. So we can cancel out the masses in this case, and that gives us V squared equals 0.7 G times R. So V equals the square root of 0.7 GR. The friction on a wet road is closer to 50%, and on an oily road can be as low as 5%. So we can see why skidding does occur on corners, particularly in wet weather. So we'll be moving on to the Check Your Learning section in the book, which is on page 109. But before that, we'll just do a quick worked example on friction and velocity. So a motorcycling rider with a total mass of 1,250 kilograms are travelling at constant speed around a circular bitumen track with a radius of 56 metres. Calculate the maximum safe speed or the maximum speed in which the car will not skid out of control, assuming friction is 0.7 times the car's weight, which is typically what we think when we've got dry road. So if we remember from the past slide, V equals the square root of 0.7 GR. So we plug in the values we've got here. V equals the square root of 0.7 times 9.8 times 56 equals 19.6 meters per second. So if we look at this, we've got two sig figs here and here, so we would give that as 20 meters per second to two sig figs as it's given here. If you're feeling really smart, you can convert that to kilometers per hour, which is the speed we normally give for vehicles. So have a go at the Check Your Learning, and also have a go at the fairly extensive chapter review on pages 111 to 113. Good luck!